We had a test. Hopefully it went reasonably well. One thing that Aaron asked me about before the test was on 3738, the last parts. It actually isn't a difficult process of going through the conversions there in the last part to change from one basis to another. But I didn't show you examples of it. That's why we didn't have something like that test. I think I originally had something like that written on the test and took it off because we didn't cover that.
37s makes sense, but 38.
So we are starting in now with the hydrogen atom. This is the reason you're taking the course, right? Everything up to here has been building up so that we can have some understanding as we go through this. So the hydrogen atom, I have a whole bunch of stuff here on the first page that we're going to use, but let's do something else.
Also a question, is there going to be homework this week?
Don't think so. I have to check to be 100% certain, but I don't think so. There'll be homework next week, though.
Looking forward.
Right. Good. Well, because, today's our introduction to it. There's not much you can do after one day's lecture. So, what is the Hamiltonian equation? How do we make that? The Hamiltonian operator, if you will, is equal to what?
Negative HY squared over 2m dBx plus the potential energy.
And so I'm going to put a V hat over there for the V operator. So that's always been what we've been doing. Or another way of saying it is the kinetic energy, that's not a T, it turns out. The kinetic energy operator plus the potential energy operator. What is the potential energy function for a hydrogen atom? So now I ask function, not operator. And I'm going to draw a picture here just to make sure we're all on the same page. And you guys know this picture obviously very well. That's basically the configuration for a hydrogen atom. You have a proton, you have an electron separated by some distance r. What's our potential energy function?
A divided by r squared.
There is a divided by r squared. Playing 20 questions today. Or maybe we're playing Jeopardy, I don't know.
Is it the charge 1 times charge 2?
Okay, except for one thing. It's not over r squared. Force is over r squared. Potential is over r. I didn't think about that until later. And so in this case, the nucleus has Q1 equals plus E. The electron has Q2 equals minus E. I wrote this over to the left a little because it's only a function of radius. So it's what we call a central force problem or a radial force problem. The potential energy which comes from the force only depends on how close it is to the center. And so we have complete symmetry in this potential energy in terms of position. If you have spherical symmetry in it, if it's a distance r away, it doesn't matter what direction, it's going to have the same potential. So when we put this into our Hamiltonian, we're going to have the potential energy only depends on R, and that's going to mean that spherical coordinates are going to be the easiest way to solve it. So this here is called the Laplacian. That's an L. And it looks oh so simple in Cartesian coordinates and oh so complicated in spherical coordinates. But we're going to use spherical coordinates because we have a spherically symmetric potential function, which means that spherical coordinates are always going to make it easier to solve. So first half of today's lecture, or facsimile thereof, we'll be going over that spherical coordinate action. So the only difference in the one-dimensional Schrodinger equation and the three-dimensional Schrodinger equation is that our spatial derivative is now three-dimensional spatial derivative. We are going to replace d dx with the gradient, which is I hat d dx plus j hat d dy plus k hat d dz. So our momentum, I swear this is supposed to be muted. Sorry. I turned it on this morning so I could have it say what time it was when I got up. That's what happens. My fault. So our momentum operator, what was our momentum operator before?
I haven't memorized these because they're on the test.
Go ahead, blame the teacher. You don't require such of us, so I haven't done such. It's okay. I don't have it memorized. Well, okay, I wrote it down. I didn't bring my book, so I guess I do have it memorized. But that was what we had before. Now we're going to have the momentum operator becomes h bar over I times that. And so it's going to have three components: the x component, the one with the I hat, the y component, the one with the j hat, and the z component, the one with the k hat. We're also going to have angular momenta now. In one dimension, there is no such thing as angular momentum. In two dimensions, there is. Angular momentum is R cross P. Now, this is not part of today's lecture, so I was going to continue on and do that, but that'll just put us behind in the rest of the lecture. So we'll get to that later. Cross products. Yeah, we'll do it later. It's an important thing, but I just can't stop. Commutator relations between position and momentum are interesting and important. Why are commutator relations important?
They show up in our different equations.
I respect your answer. Up to this point, you're like, well, they've shown up in equations. So
Well, like in the uncertainty principle, to find the commutator allows you to find the uncertainty relation between two objects.
yes, and that actually is what I was going to. It tells you, for instance, if you can know two variables simultaneously. You know, we've been finding the solutions to the energy states, right? And that's what we're going to do here. We're going to go back to the Hamiltonian and find the solutions to the energy state. Well, what can we know simultaneously with the energy? And so we're going to check commutators to see, can I know the energy and simultaneously know what the position is? No. Can I know the energy and simultaneously know what the angular momentum is? I can know what the magnitude of it is. I can know what the component in one direction is, but I can't know the other two components. So it's the commutator relations that allow us to determine that. So that's a really important thing from the commutator relations. So let's calculate this. What is the commutator between now, instead of x and p, I have r sub I and P sub J. So this could be, for instance, X comma P sub X, X comma P sub Y, Y comma P sub X, etc. Right? All of the different options. So you have a total of 6. I wrote down, is it 6? No, 9. Total of 9. I wrote down 3. We'll only calculate probably 2. So what is XP of X? How would we calculate that?
Well, the normal way.
Right, the normal way. This is XPX minus PXX. If we throw size on there, then we're going to have X H hat over I ddx psi minus H hat over I d dx of X psi. Okay, these other two, I've got to erase them because they clearly can't fit all my work in that close together. Equals H bar over I x d psi dx minus H bar over I x d psi dx minus H bar over I psi. So I had to use the product rule to get those two terms. And then we say, wow, this one here and this one here are identical, so those add to 0. Did that in my previous class too. I must be allergic to teaching today. So we have X comma PX equals minus H bar over I. And that should be, did anybody bring their textbook? I didn't. That should be what we have in the front cover. I think easier way of writing this is IH bar. And if we did Y and P sub Y, what do you think we'd get? We did the commutator between Y and P sub Y.
Still IH bar.
It'd still be the same thing, right? And so we don't have to do Y P sub Y or Z P sub Z because they're going to be the same. But then we have to do X P sub Y. So if I do X P sub Y, commutator between them, what do I get now? When I do a partial derivative with respect to Y, what is X? Not 0.
Oh, 1.
It's just a constant. X is just a constant when I'm doing a partial with respect to Y. That's the key about partial derivatives. And so the X just comes through as a constant. And so these two terms are identical to each other. I didn't have to use any product rule here because X was a constant, and that's equal to 0. So I have X P sub Y commutes because commutator is 0. And what about X P sub Z? That also commute, right? So we have some simple commutator relations here between position and momentum. So we can know the position in the x-axis and the momentum in the y-axis simultaneously. We can't know the position in the x-axis and the momentum in the x-axis simultaneously. We know perpendicular directions simultaneously. Okay, getting back to the gradient. Here's the Cartesian coordinate version of the gradient operator, as I already showed to get the momentum operator. But the Hamiltonian has that squared. So that squared, you just do the dot product. And so the dot product, the x component times the x component, it's going to be d dx acting on d dx. That's the second derivative with respect to x. And then y with y, that's second derivative with respect to y. Z with z, second derivative with respect to z. That was real simple. We really like to do problems that have, Cartesian coordinates with this Laplacian operator. Makes life easy. So, for instance, a problem that we didn't do, we might get to it later, but I don't think so, is a problem where you have, a square grid lattice. Basically, it's like a particle in a box in 3 dimensions. And if you have particle in a box in 3 dimensions, the x dimension, the y dimension, z dimension are all independent, essentially, and you just have 3 solutions for the particle in the box. And it comes out real quick and easy if you know how to do the particle in the box. Not so much here. Here's the Laplacian in spherical coordinates. So in spherical coordinates, we have the radial direction with the r hat. We have the altitude angle with the theta hat, and the azimuth with feet. So what's the difference in altitude and azimuth? The azimuth is going around a circle, 360 degrees. The altitude is from going up to going down, 180 degrees. And already one starts to say, well, this looks really crazy. I thought we were dealing with a simple spherical symmetry. Our potential function was really simple. Why is it so crazy? Well, because, let's just say because that's the way math works. So now we have to do the Laplacian del dot del. And so we take the r component acting on the r component. So I didn't write out the long form here because you know what, it's really long. But I have this DDR acting on itself, and I get this crazy thing here. Now you look at it, you're like, how did he get this crazy thing here? Right? That doesn't look like second derivative with respect to r. Ones are more annoying. You have 1 over r d theta acting on 1 over r d theta, and it gives you this crazy stuff. So you can see that there's more complexity going on here. We're not going through the math. I think you had to do this in Calc 3, didn't you? So a lot of what we're doing today, we're relying on other people for math. We're not going to do all of the math ourselves. We're going to take some faith. And trust me, when we get to the spherical harmonics and you see the Rodriguez formula, you're just going to be saying, well, thank you, Mr. Rodriguez. You made my life a lot easier because I didn't have to do that. So how do we use this? Well, here's the Hamiltonian. The Schrodinger equation, actually. The Hamiltonian is just, Here's the Schrodinger equation. Happy times, right? I mean, what could go wrong? This is the time independent, by the way. We did want to make it easy on ourselves. You see how easy this is, right? What do you think we should do? Let's just brainstorm. Obviously, I know the answer. But what should we do?
Separate.
Yes. Does it say that?
What was that? I mean, that
Oh, it says at the top.
Too simple.
Doggone it. I was like, man, he is on point. We want to separate variables. We want to try to break this down into some smaller equations, just like we did to get this time-independent equation. Remember, we had the time-dependent Schrodinger equation. It had both time derivative and spatial derivative. And what did we do to get the derivatives separated to get this time-independent version?
Yeah, kind of.
Well, that's true. That's true. We said that our wave function is going to be a product of a function with time and a function with position. And furthermore, we said that could only be true if the potential energy function was only a function of position. If it was a function of time, we couldn't do that separation. So we're going to try the same thing here. We're going to say, okay, let me suppose that psi is, now how many variables does psi have in here? 3. Doesn't have time because we've already split one out. So we're going to say let psi be a function of radius times a function of the azimuthal angle times a function of the altitude angle. That seems good, right? We're going to start out by combining these two here into something that we'll call y. Y of phi and theta. And so we're going to start by just having the radial part and the two angular parts. And of course, that's what I have right here. That's a y. The font set made a funny looking y. It looks more like an upsilon than it does a y to me. So, I hope I pronounced that right. So we're going to make that substitution. So if I make that substitution, abracadabra, it simplifies to this. Now, this has been, I got 25 minutes. I should probably do it. If I put this in, there's the first term. There's the second term. There's the third term. Our v sub r, we've already seen its function. There, I've put the whole stinking thing in. And we notice that this is taken derivative of with the r vector, or excuse me, the r variable. And so since it's a partial, this is a constant in terms of that derivative. If we go to the next one, we have derivatives in theta. So this is a constant in terms of the derivatives of the second term. Derivative with respect to phi, this is a constant. And then there's no derivatives in any of these. So what we're going to do is the same thing we did when we separated the time from the spatial parts of the Schrodinger equation. going to divide all of the terms by psi. And so if we divide them, the constant ones will divide out. So I'm going to have, I have to put the r of r here. That won't divide out because the derivative depends on it, but that will divide out. This one here, I'll have to put over y. I'm going to start putting the rest of the variables. This one here, I'll have to put over y. This one here, they both cancel out. And this one here, they both cancel out. What was the point of that? What variable is in that box? R. What about this box? Oh, I see something else I should have done. I should have multiplied everything by r squared as well. Multiply everything by r squared so that this cancels, that cancels. Okay, so now that I've canceled the r squareds, what do I have in my cyan box? I have y. And what about this brown box? And then what about this green box and this green box? Okay, so I have three terms, the black one, the two greens that are just R, and two terms, the brown and cyan that are just Y. So that's what this is doing here. It's separating out the things that had R in them and the things that had theta and phi in them. So and notice it is multiplied by the R squared that I had forgotten initially. So this side only depends on R, and this side only depends on theta and phi. How can this be true? How can I have a function of R equal to a function of theta and phi for all variations? Only if they're both constant. And so we're just going to set this equal to a constant. And now is where hindsight is super important. We'll call that constant, L times L plus 1. That seems reasonable, right? I mean, I could have called it capital A, but L times L plus 1 just seemed a lot more reasonable. And so that's why I have my comment here that for reasons that will only make sense later, we define each side of the preceding equation as equal to L times L plus 1. So we now have two equations. So now I have this equation that's the function of R, and this one here that's the function of theta and phi. Now we're going to set the R equation aside and concentrate on the theta phi one for today. The R equation will come back to, tomorrow. So this theta and phi equation, it has two variables. What would you like to do if we have a function of two variables? Go ahead, Chad. Split the variables just like we did. We just split R away from theta and phi. Now we'd like to split theta from phi. So if you think about it, we started with four variables. Time, R, theta, phi. We split out the time a long time ago. Now we're doing the same process with a much harder outcome. So we split the R away, and now we want to split theta and phi. So how do we split theta and phi is the question. Well, with this lower equation, you do notice that this here is only dependent on theta. This here is dependent on phi. It also has a theta there. So if I multiply everything by sine squared theta, then I can have this one here that's just a function of phi. So I'm going to multiply everything by, well, first, let y equal to capital theta of theta and capital phi of phi, and multiply by sine squared theta here. And what I'm going to have is sine theta over capital theta of theta d theta sine theta d capital theta. Notice I let the phi ones cancel out here, so I didn't write them. Because the partial derivative with respect to theta, the phi is just going to pass through as a constant. So that's my first term. My second term, remember I multiplied by sine squared, so there's no sine squared. D second phi, d phi squared, and I have a 1 over phi out front. The theta canceled out, equals minus sine squared theta L times L plus 1. Actually, I'm going to change this last one to be in a different color. Yeah, black. So now the black one and the green one only depend on theta, and the magenta one only depends on phi. So we've done what Chad said. We've separated them once more. So let's just go ahead and move this over here. So we're going to have this one's positive, the other side's negative. And that gives us, well, we've already gotten to this point. Gives us this. Actually, move the minus sign to the opposite side. And we set this equal to m squared. Why m squared? Because b was too hard for us. M squared much easier. As you probably perceive, once again, when we get to the end, m squared makes sense to come back and say that constant is equal to m squared. I am sure the first person who did this used a and b, got to the end and said, oh, well, a is equal to L times L plus 1, and b is equal to m squared. And so we're like, why not just put it up easier? So now we have this equation here, actually, because if you look at this later, it's better to see it here. This equation here equals m squared, or this equation here equals m squared. Which of those two would you like to solve first? The red box or the magenta box with it equal to m squared? Thank you. The red box, as I say, is almost trivially easy. This is called the azimuthal equation. And this is second derivative, once again, from differential equations. By this point, you probably recognize that second derivative is going to be an exponential form. And so you put e to the b for psi, or for, well, let's just do the work. Let's just do the work. So it has that form. So that means the second derivative of this. Now, why did I change in the left from partial derivatives to exact derivatives?
Because that's the only variable.
Yeah, because there is no difference when there's only one variable. Sometimes you look at this and you think, man, I don't even know how we changed from one to the other. And as teachers, we often, like we've seen so many times, it just flies by us and we don't think about it. But it's important for the student for there to be reason in what we do. So that's why I asked you the question. So the second derivative is just going to be b squared times phi. So if I put that in, I have b squared phi. Let's just put it here. B squared phi equals minus m squared phi. And then you're like, so what could b be equal to? Well, if we square root both sides, right, we have b squared equals minus m squared. If you square root both sides, you have b equals plus or minus square root of m squared or minus m squared, or plus or minus im. So we have two solutions, plus im and minus im. Now we can start to say, hey, I can see where that m squared was useful, because that's what we have for our exponent. Now we have boundary conditions. Boundary condition is simple. If I am doing my azimuthal function, I start here, it can change continuously, but when I get to here, I'm back to where I started, right? So it has to be back to where I started when I go around. So we call this a periodic boundary condition. You have to have phi of 0 is equal to phi of 2 pi. It has to repeat on itself. And so, since we have e to the plus or minus im phi, what's another way we could write e to the plus or minus im phi? Let's just do e to the im phi. What's that equal to?
Sine or cosine.
Forgot the m. So you have to have that cosine of 0 equals cosine of m times 2 pi. And likewise for the sines, I'm just only doing one of them. And how is that true? Well, this would be true, of course, if m is equal to 1, or if m is equal to 2, or if m is equal to 3, etc. So we have m must be an integer. What if m is 0? Would it fit here? Would cosine of 0 equal cosine of 0? Yeah. And likewise, sine of 0 equals sine of 0. So it doesn't violate here. What would that make my phi function if m is 0? This is our phi function. If m is 0, what is that? 1. Now, when we start out, would 1 have been normalizable? Normally it would be. If we went from minus infinity to plus infinity, it wouldn't be normalizable, right? It would be infinite, because it needs to go to 0 as you approach s equals plus or minus infinity. But here we're not going from plus or minus infinity, or from minus infinity to plus infinity. We're going from 0 to 2 pi. So to normalize, we're just doing the integral from 0 to 2 pi. So the integral of 1 from 0 to 2 pi is 2 pi. Divided by 2 pi, and you can normalize it. So it's allowed to have m equals 0. If m is minus 1, well, we had plus or minus m up there. Obviously, we could have m being plus or minus in our outcomes here. So at this point, we'd say m is just any integer, positive or negative, including 0. I said at this point. Now the other one, the altitude equation. This one, not so simple, which is why I asked the question. Was very thankful that Aaron, like me, said, let's do the one that looks simpler. So how do I solve this? And you notice my subtext. We rely on the mathematical achievements of others. People who, quite frankly, are much smarter than me, at least in the math realm. And so people have found that the solutions are the associated Legendre polynomials. What are the associated Legendre polynomials? Well, it's simple. You have the derivatives of the Legendre polynomials. That's why they're associated Legendre functions. They're associated because they're associated with Legendre polynomials. And how do you get those Legendre polynomials? Well, duh, you just use the Rodriguez formula. So, what are these things? Here's the Rodriguez formula. So here's our Legendre polynomial, P subscript L, as a function of x. Okay, so we're not going to use x. What are we going to use for our variable? Theta, right. So we're just going to put theta everywhere. There's an x here. 1 over 2 to the L factorial. The nth derivative with respect to x of x squared minus 1 raised to the nth power. That's simple enough, right? Okay, let's start with things. We have 1 over L factorial. What immediate limit does that set on L? Has to be greater than 0. We have a derivative, the nth derivative. What does that tell us about L? Here's a clue. Could you take the 1.75th derivative?
I don't think so.
I don't think so.
Not great.
L has to be an integer. L has to be an integer. Now, I come back to the factorial. The factorial function is actually only defined for integers as well. So L has to be an integer that's greater than or equal to 0. It doesn't say here that L has to be greater than or equal to 0. So Chad, you totally nailed that without something here that would have told you the answer. Yeah. So we have some restrictions on this L value. Now, this is why we have the L times L plus 1, because it gives us these values in the polynomial. Imagine if we had just said capital A, and then we would have this associated Legendre polynomial, the Legendre polynomial, and we would have, how would we even get A from L times L plus 1? Right? It would be really complicated for what we have factorial and for what we have for the number of derivatives. So that's why we take the knowing the answer and going that way. Now let's think about this a little. This polynomial, we take the nth derivative of x squared minus 1 raised to the nth power. What is the highest power of x we're going to get when we take that nth derivative of x squared minus 1 to the L power? I'll start this out by saying, if you expand x squared minus 1 raised to the L, your highest power is going to be x to the 2L. And then you're going to have each power between that and 1. So if we have our highest power as x to the 2L, and we take L derivatives, what's our highest power going to be? Not 1. Well, let's put numbers in this. We have, let's say L is 7. So that means we have x to the 14th, and we take 7 derivatives of it. What's the power going to be after 7 derivatives if you have x to the 14th? 7. Right? You come back to L. So we're going to have the number of terms here is going to be, well, the highest power will be L when we do that polynomial. And of course, the 1 over 2L L factorial is something that's just going to give us glee and joy as we go through life. Now, the associated Legendre function, and Legendre, French names, we learn to pronounce them. Now, notice it has L and M. So P subscript L superscript M is equal to 1 minus x squared raised to the m over 2 times the absolute, and this is absolute value of m over 2, so if m is negative or positive, doesn't matter. The absolute value of nth derivative of this function. So we took that derivative L times, and we're left with x to the L power. And now we take a derivative m times. How many times can you take a derivative of x to the Lth power and not end up with 0?
How are M and L related to each other?
That's what we established when we answer this question.
L minus 1 or something? I don't know.
Well, let's once again just put simple numbers in. Let's say we had x squared, that is L is equal to 2. How many derivatives can you take before you get to 0? If I take one derivative, I have x. Two derivatives, well, I have 2x. Two derivatives, I have 2. Three derivatives, I have 0. So I can take two derivatives. So the number of derivatives I can take, the maximum number of derivatives I can take and not get 0 is equal to the power of my highest power of x. So since my power of x is going to be L, that means I can only take up to m equals L derivatives. And so that sets your relationship. Now, once again, because we're taking derivatives, the number of times that m has to be an integer. Right? You can't take the 1.75 derivative. And we have, based on these two relationships, the restrictions that, okay, this one gave us a restriction, L is greater than or equal to 0 and integer, right? That's what we got from the first one. And the second one, we have absolute value of m is less than or equal to L. And so now we can say, m is equal to minus L plus 1, 0, L minus 1, L. Those are the possible values you can have for m. Now, you've had enough chemistry. You already know this from what you said in chemistry, but you didn't see any reason for it. It was just given. Here's the reason. It comes out of the math of solving the angular function for the Schrodinger equation for a hydrogen atom. And in fact, anytime you have a central force that is a potential that only depends on radius, you're going to have the same L and M, the same meanings, the same restrictions. So I'm going to have to stop here because of time, but this is a very cool stopping point because we can see something that you already knew applying for years. See, while we don't understand how the Rodriguez formula was derived or why the associated Legendre function is used, we can see that with those two, we have these restrictions that we have seen over and over and over in our chemistry. And we'll learn about what L and M mean soon enough.
Do the P's mean polynomial?
Honestly, I don't know. It obviously doesn't stand for Legendre.
Yes.
It probably stands for polynomial, but I honestly don't know.